Thanks everyone, thanks Lorenzo for being here. Welcome to our last seminar of OLOFOS Seminar, last of OLOFOS Seminar. And today we welcome Lorenzo Rossi, who's going to give a talk about Supervaluational truth and quantifier. Lorenzo, thanks again, and the floor is yours.
Thank you. Thank you so much, Landine and Peter, for having me here. It's a great pleasure. And so this is a joint paper with Johannes Stern from the University of Bristol, and it's very much work in progress. I think it's actually two papers rolled into one, so you will help me to disentangle these two things. And really, thanks everyone for being here and for having me. Okay, so the plan, let me be a bit more light. Yeah, the plan of this talk is to extend a well-known framework to deal with indeterminacy, which is a supervaluational framework, to quantifier semantics. And by this I mean to deal with generalized quantifiers. So in general, quantifiers that cannot be defined in first-order logic, such as finitely many or most. Okay. And there's many sources of indeterminacy. Here in this talk, I will just focus on three, which I think lend themselves rather naturally to be dealt with within the supervaluational framework. I'm sure there's possibly many more. And here they are presupposition failure, vagueness, and various phenomena connected with semantic paradoxes. So we have foundedness, paradoxicality, ungroundedness, and such. Okay. So, as I said, the goal is to extend a supervaluation semantics, which isn't quite a textbook supervaluation semantics, is a tad different, hopefully a bit more general, to generalized quantifiers, because we wanted to explore the supervaluation treatment of these three things. So, supervaluation treatments are presupposition failure, vagueness, and paradoxes. Now, I have been working mostly on theories of truth and paradoxes for a long time, but I've forced myself to have exactly one slide on semantic paradoxes, which isn't even about paradoxes, about the truth predicate. So it'll be one slide, and of course there is an appendix with the other slides. So if you have questions, you're welcome to ask. So the result, as I said, is actually not one semantics, but two, and they are competing because I think in the end there's a genuine trade-off between them. But in both of them, desiderata concerning these three sources of indeterminacy can be arguably met. And there is a substantial fragment of GQT, which is my abbreviation for, or the abbreviation that I use for generalized quantifier theory. So there is a substantial chunk of the theory of generalized quantifier is recovered, and we're going to characterize precisely as best I can this fragment. Okay, so here's the outline. There's a lot of slides, but don't worry, the talk is much shorter, and here I have an appendix, three appendices for details. So let me start from the setup, which is a roughly Fregean picture. I don't claim to be philologically accurate. I have no clue whether Frege would agree, but this is Frege inspired. And the Frege inspired picture is the distinction between concepts and higher order concept. So in this distinction, a concept, not to be confused with the psychological notion of concept, is a function from individuals to truth values. And higher order concept is the same, pretty much, but one level up. So rather than a function from individuals to truth value, you have a function from concepts to truth values. And we are located at that level, because quantifiers are higher order concept. So to give you an example, consider the quantifier every. The quantifier every is the function that takes two inputs, two concepts, let's say dog and friendly, and outputs the value true if whenever dog applies to an individual, so does friendly. So this shows that every dog is friendly is true. So you feed it two inputs, and whenever something is a dog, but that individual is also friendly, if it's true, then the quantifier is also, the quantifier sentence is also true. Okay, so of course, this is the classical picture, and in the classical picture, whenever you have a concept, you have two possibilities. Either the concept applies to an individual or its negation does, right? So this is exclusive and exhaustive. However, if you have indeterminacy around, it's not obviously the case. I mean, it might still be depending on your treatment of indeterminacy, but at least it's possible that this is no longer warranted. And in general, there might be a partial, which here I take it to be synonymous with trivalent, interpretation of the language, whereby a concept can be a partial function. Right? So you have that C applies to an individual, that not C applies to an individual, or that neither happens. However, and this is the usual, run-of-the-mill supervaluational motivation, if you say that you are content with a single partial interpretation, whether for any given concept C, either C applies or not C applies, or there is a gap, right? It means that you have a very precise way of drawing the line, right, between these three cases, between C, not C, and the gap. But it might be that there isn't a preferred way. If you take a vague predicate, for example, is the usual motivation, there's many possible ways of drawing the line, and you might want to respect some clear cases, but the borderline cases admit many different ways of drawing the line. So, to the supervaluationist eyes, this suggests considering not just one interpretation, but many. All those that are compatible with your existing semantic information. Maybe you have some information, you want to preserve that, but then after that, you can specify in however many ways you like. So the idea here is, of course, you combining these two strategies, trivalent semantics to begin with, and supervaluations later. Okay. Now the usual picture is that, one usual picture is that in a supervaluationist semantic, you start from a trivalent interpretation, and then you make precisifications which are bivalent themselves, right? So they are classical. Here, we're going to relax the assumption. Our precisifications may be trivalent themselves, maybe are more informative than the one you had to begin with. Maybe the gap is actually smaller in the sense of set theoretical inclusion, but they are allowed to be trivalent. They needn't be. They can be classical. So if you like the classical approach, it's perfectly compatible with what I'm going to say. So the issue, of course, is that as soon as you apply this picture to the level 1 concept, it also applies to level 2, higher order concepts. Quantifiers can be partial too, right? Every dog is friendly is true in a given interpretation if, as I said, whenever dog applies to an individual D, so does friendly. But supervaluation of truth requires considering all compatible interpretations, right? Because you don't have just the friendly individuals and the dog individuals in your domain. You have many possible extension until extension gap. So every dog is friendly must hold in every partial interpretation compatible with the given one. Again, if you are more classically minded, just remove the word partial here and you have a standard supervaluational picture. So classically, every dog is friendly is false if it isn't true. So if there is one individual in your domain, which is a dog but not friendly. But of course, with partial concepts, you can have interpretations in which dog is not a subset of friendly, so they do not stand in the subset relation, but there isn't a counterexample, there isn't a counter-witness, right? Simply because the counter-witnesses only belong to the gap. So no individual is both dog and not friendly. So this suggests that we also need, if we are going to give supervaluational truth conditions for quantifiers, separate falsity conditions. And this is also not a surprise for many of these non-classical semantics. You need truth conditions and falsity conditions. Okay, so this is the setup. Now, before going to the specifics of the semantics, and I'm also going to, perhaps in the interest of the discussion, to skip some of the details because they're not so relevant for the big picture. I would like to offer you a couple of possible semantic judgments concerning quantified sentences and inferences in the case of indeterminacy. These are quite controversial, so I've had many different responses to this example. Some people think inferences go through or judgments are true, or maybe they don't. But the answers to these judgments will help me to adjudicate between the two competing models that I'm going to produce in the end. Okay, so one thing that is sometimes discussed in the context of indeterminacy coming from presupposition failure is failure of contraposition in a quantified setting. Okay? Consider the first sentence. Everyone who quit smoking was told by their doctors to quit. We have a presuppositional verb, quit, so it assumes that the person was smoking. On a very standard trivalent semantics for presuppositional verbs, quit smoking is true if the person was smoking and then doesn't smoke, is false if the person was smoking and then still smokes, and is indeterminate if the person was never smoking. Okay? So this seems like a true sentence, but this sentence seems not true in the sense that, well, everyone who was not told by their doctor to quit smoking did not quit. I am a counterexample. I never smoked, so I was never told by my doctor to quit smoking because my doctor never needed to tell me to quit smoking because I never smoked in the first place. So this is true, but it's false that I didn't quit if you adopt this particular semantics for quitting, right? Because did not quit is indeterminate, it's not true. You might think that this is a good counterexample, you might think this is not. As I said, people have a lot of different reactions to that, but this is one possible motivation failure of contrapositions coming from presupposition failure, to have this sort of indeterminacy behavior in quantified inferences. Another one, this is probably less strong, is motivation category mistakes, also motivating failure of contraposition. Every expensive thing is on Earth, seems about right. But if you say everything not on Earth is not expensive, depending on what you mean by not expensive, you might think that this is false, because items that are not on planet Earth are not for sale. So expensive and not expensive don't apply. Now the classically minded people will say, wait, not expensive is the complement of expensive. It doesn't mean cheap. Other people will say not expensive means cheap, because there is a presupposition that you're only talking about items for sale. So depending on which of the two views you adopt, you might like or not like that inference there. There's also a failure of contraposition for quantified claims that has to do with failures of contrapositions in conditionals. It doesn't revolve around the form of indeterminacy that we have here. But if you're familiar with these counterexamples to classical inference in conditionals, you might see them with every, for example. Every person who orders a drink doesn't order wine. That might well be true in a given scenario. There are people who order a drink and none of them goes for wine. But if you say every person who orders wine doesn't order a drink, that's obviously false, because wine is a drink. Okay, so the first semantics I'm going to propose actually doesn't validate contraposition. So if you want these counterexamples to be counterexamples, then maybe the first semantics is the one for you. Other kind of linguistic phenomena that we might want to look at are cases of homogeneity in definite plurals. Suppose that there are 4 kids, 2 of them are asleep and 2 of them are awake. And consider the first sentence, the children are asleep. True or false? People tend to hesitate. How about the children are not asleep? The first one were false, then the second one might be true, but is it true? 2 of them are asleep and 2 of them are not asleep.
Also false.
That's one judgment that you find in the literature. And so the idea is that here people tend to hesitate and say, well, we have an exact symmetry between the 2 cases, so neither of them are acceptable. How about, this is optional, but how about the children are either asleep or not asleep? There's 2 readings, right? You can read this in a distributive manner. So for each given kid, that kid is either asleep or not asleep. Or you can read that in a collective manner, so that all the children are asleep or all the children are not asleep, which would be false. So depending on your judgment, but these are cases that are discussed in the literature of indeterminacy and quantifiers. I should mention the definite article is a quantifier. It's treated as a generalized quantifier in generalized quantifier theory. So this is why this is quantification of indeterminacy. And then my favorite example, anti-restrictors. So context, my colleague and friend Matteo is in charge of interviewing the foreign applicants to our MA program. This is true. And we have no Faroese applicants. Also, I think it's extremely rare to have a Faroese applicant because there are so few of them. So sentence 1, Faroese applicants are interviewed by Matteo. Well, this is a bare plural, right? So also a quantifier. If you work in generalized quantifier theory, everything starts looking like a quantifier. So many things are quantifiers, but that's a bare plural. So it is. And that's an empty restrictor, right? Because there are no Faroese applicant. And since this would go with the semantics of the subset, the empty set is a subset of everything, so it would be true, classically. But it would also be true that Faroese applicants are not interviewed by Matteo. So if you adopt the classical semantics, you can replace Faroese applicant with every Faroese applicant, if you like. They're both true. And that seems weird. I mean, in particular, it seems that since Matteo is in charge of interviewing all the foreign applicants, if we have Faroese applicants, well, the first will always be true, because in case we have them, they're interviewed by him, and the second one turns out to be false. So these are all like non-classical features of inferences involving quantifiers that sort of motivate a supervaluational treatment, because all these inferences turn out to be treated non-classically in the semantics that I'm going to propose. In particular, the semantics I'm going to propose, it's possible that this is true and this is false. Okay, so these are motivating examples to get a sense of the kind of linguistic phenomena that, as I say, motivate our work in the first place. And now let me go to the formal semantics. I'm going to skip over some details because there's a lot of ugly formulations that we haven't been able yet to make more elegant, but I'll give let's say the informal descriptions. So what is an interpretation for us? We start from an empty domain, and then we take any function that behaves just like an interpretation in first order logic, so no funny business. The interpretation of a term is an individual, the interpretation of a function is a function. The only thing to bear in mind is that the interpretation of a predicate is a pair, because it's an extension, anti-extension pair. So we leave the possibility for there to be a gap. Okay. Okay, so this is the first member of the gap, that's the second, of the pair, that's the second member. Importantly, these interpretations are partial, so we don't assume that if you take the union of extension and anti-extension, you end up with a domain. Okay, now for introducing gradually the supervaluational component. Suppose you have two of these interpretations, right? So here's one interpretation, what kind of object it is, and suppose you have two. We say that they stand in the ordering relation. We write that I is before j. Just in case, basically the inclusion in the positive and negative clause is preserved. Okay, so basically j agrees with I, okay, on the positive cases and agrees with I on the negative cases. Okay, so you can think of it as a precisification, right? We just don't assume that precisifications are classical, but other than that, it's just supervaluationism. Okay, now once we have this at our disposal, we view the space of precisification as if it were a modal structure. Okay, so you can think of that as a frame, essentially. So you have an empty domain, you have a set of interpretations, and your set of interpretations don't disagree on the individual constants, so you might think as a constant domain, first order model semantics. And then you have an accessibility relation that basically, at the very least, tracks the extendability relation, the precisification relation. So, and you can view the objects in our modal space as interpretations. So a world can be an interpretation. And the accessibility relation between worlds is extending or precisifying. Okay? So obviously this is reflexive because you extend or precisify yourself trivially, and it's transitive because if you have one interpretation that extends a first one and a third that extends a second, and the third one extends the first one. Okay.
So, one question for clarification. Why is it not just this relation small or equal then? But the h, which...
Because we wanted to leave some space for just taking a having the accessibility relation in each model changing from this, but it's completely unnecessary, in fact. So nothing bad happens if you identify h and the lesser than relation. So you can...
It would be interesting to see if there are cases that...
Yes, there are cases where this is required by some applications to the logic, but not quite to the quantifier cases. So not quite to the cases that I'm going to consider. But so you're right, and for the particular purposes of today, they actually can be safely identified.
I see.
Yeah. Okay, this is supervaluational structure, and now remember that we want to talk about quantifiers. So we need to go to the right level of generality, or sorry, of concepts of concepts, and in particular we want to single out the domain of quantification. So suppose that we have a supervaluational structure, and let's consider the set of all the functions from the interpretations, okay, because remember it's a concept of a concept, to the power set. And you can also view it by its characteristic function, to truth and false, doesn't really matter. And what is a quantifier in our case? Well, is a subset of this particular space. So here we have the space of all the functions that go into the power set of the domain to the power of n, to the Cartesian power of n. And here we have all these functions. Okay, it doesn't matter what the arity is here. And a quantifier, okay, would be a subset of the Cartesian product of all these domains. This is only because we are dealing with functions rather than with subsets. So if you have in mind, let's say, the classical generalized quantifier picture where a quantifier is a set of sets, okay? For example, let's take the type 1,1 quantifier every. Classically, every is the set of all pairs AB such that A is a subset of B, right? So it's the extension of the subset relation. In generalized quantifier theories, quantifiers have an extension. They're not syncategorematic expressions like in Tarski and semantics. And here you have that the relation in question is a subset relation, okay? And you take all the pairs such that A is a subset of B. So every contains the pair dog friendly, cat shy, whatever you want, okay? Here, however, we need to deal with functions. And so for us, quantifiers are pairs of function, fg, okay? Such that whenever you apply the function to an individual, the result has the property in question if and only if the second function applied to an individual has the property in question, okay? So that's the Fregean picture that we were starting from. So remember the example, every dog is friendly. So whenever you apply the first function here that is the function associated with the concept dog, here friendly, and then you preserve inclusion. Okay. This is a presentational difference that is essential to this way of spelling out things. However, in the end, we are also going to work extensionally with these functions, so you can think of them as sets, basically. Okay, and as I already anticipated, we are going to consider the so-called type 1-1 quantifiers. The type 1-1 quantifiers are those exactly like every, whose extension is a set of pairs. Okay? The type 1 quantifiers would be those whose extension is a set of sets, like everything, something, infinitely many things, and so on. You see the pattern here, that there is a quasi-logical word thing that does the job. Essentially everything, okay, is the set of all sets that coincide with the domain. There is a singleton of the domain. The extension of everything is the set of all is the set of all sets that are non-empty. Right? Because something is A is true if the things that are A are the non-empty set, a set that is non-empty. Okay? So basically, something is the collection of A such that A is non-empty. But if I take some, this is the type 1 quantifier and this is the type 1-1 quantifier, this is the collection of pairs A, B, such that A and B have a non-empty intersection. So if I say some dog is friendly, well, that is the pair dog friendly belongs to the extension of some because the intersection of dog and friendly is non-empty. So you take all of them. Okay? And we are going to focus on the ones whose extension is a pair. The reason why we focus on them is that linguistically they're very prominent. They correspond to the syntactic category of determiners. So you can also view that something is a special case of sum, where you just fix one of the two arguments to be the whole domain. The same for everything, and so on. So those are the ones that receive a lot of attention in generalized quantifier theory. Other quantifiers do too. And in fact, an arbitrary generalized quantifier is an object of type nk ... nj. So it can be 1, 2, 7, 3, blah, blah, blah for a finite tuple that is as long as you like. But it's very difficult to find an object in natural language that corresponds to that particular quantifier type. Whereas type 1-1 quantifiers are extremely common. So they're very linguistically prominent. Okay, and I'm going to impose a further restriction on the quantifiers that we are going to consider, which is the so-called conservativity requirement. The quantifier is conservative if that happens. A pair Fg belongs to the quantifier just in case the pair F intersect G belongs to the quantifier. You already have some examples on the whiteboard. Every is conservative, some is conservative. So every bike is red is felt to be equivalent to every bike is a red bike. Or some person has an umbrella is felt to be equivalent to some person is a person with an umbrella. So if you repeat the first argument, the restrictor, in the second argument, the scope, you don't change anything, basically. Conservativity was a property of quantifiers, generalized quantifiers, that was isolated in the 80s by a series of simultaneous work, but in particular there is a very influential paper by Barwise and Cooper who argue that conservativity is a so-called semantic universal, which by analogy with syntactic universal is something that, if it is true of the extensions of the quantifiers, so of everything that interprets a determiner, a quantifier in natural language. And this is not my field, I don't do comparative linguistics, but I know that the semantic universal for conservativity has been tested very extensively across languages that have nothing to do with each other, and has been found to be extremely robust. So there is a very strong empirical evidence that natural language expressions which denote quantifiers denote conservative quantifiers. Exceptions have been proposed in the literature. If you want, we can discuss one that is especially discussed in the literature, but the consensus amongst people working on the linguistic side of this seems to be that natural language determiners determine conservative quantifiers. So this is one reason to focus on these conservative quantifiers. So as I said, we focus on conservative quantifiers for their linguistic prominence and also the conservativity universal, this thesis that I just tried to summarize. Now, we want to give a supervaluational semantics for all these guys, for all these conservative type 1-1 quantifiers, after having motivated why focusing on them. Now, how many of these conservative quantifiers exist? Well, a lot. Obviously, infinitely many. If your domain is infinite, if your domain is finite, I think there is a paper of Van Bentham where he shows that there's 2 to the 3 to the n conservative quantifiers, type 1-1 for n the size of your domain. So there's a lot of them in general. And also we are interested in the general case where your domain is allowed to be infinite. So we need a way of constructing these conservative quantifiers, because I cannot give you a semantic theory with infinitely many clauses. That wouldn't be a manageable theory for us to work with. Fortunately, there is a beautiful result from the 80s again, by Keenan and Stavi, that provides a simple and elegant characterization of the space of conservative type 1-1 quantifiers. So essentially they show that every type 1-1 quantifier can be defined by applying Boolean operations, so intersection, union, and complement, to just 3 kinds of basic type 1-1 quantifier. So you take 3 type 1-1 quantifiers, and you give the semantics for them, and then you close your semantics under these Boolean operations, and you have all of them. Okay? All right. So the 3 type 1-1 quantifiers we need are every, so the subset relation, basically. Cardinality quantifiers, at least lambda many. Okay, so of course this is definable if lambda is finite. If lambda is infinite, it's not definable. So for every lambda up to the cardinality of your domain, you need to have the quantifier at least lambda many. Okay, and the so-called basic possessive quantifiers, like John's. Okay, like the ones that you find in these genitive constructions. This is also something that is interpreted as a quantifier. If you have them, then basically, thanks to the Keenan-Stavi theorem, you can define all the type 1-1 conservative quantifiers. Now, so the very first step to recover an amount of generalized quantifier theory in our framework, which is now exactly the amount consisting of conservative type 1-1 quantifier, we need a version of the Keenan-Stavi theorem in the framework that we're working on. Okay, which is, this supervaluational non-classical function-based framework. Fortunately, that's not complicated because there is a way of proving the theorem that makes it very abstract and purely algebraic, and so you can reproduce it in whatever framework satisfies the basic constraints. So suppose you have a supervaluation structure, and your set basic quantifier will be the set including the denotation of every, at least lambda many, for every lambda up to the cardinality of the domain, and the possessives. Now, I apologize because these look ugly, but bear in mind the much nicer looking every that I've written on the whiteboard. So the semantics for every is that one. Now it bears a superficial resemblance to that, but the spirit is the same. So rather than having all the sets or the pairs AB, such that A is a subset of B, we move to functions, but functions are supervaluated. So we take all the functions fg, okay, that live in your structure, such that for every interpretation that extends the given one, okay, so you're given an interpretation J, the sets that are outputted by applying F to J is a subset of the set that is outputted by applying G to J prime. So remember, every dog is friendly. It has to be that for all the interpretation, if this outputs a dog, then if this outputs a set of individuals, that set of individuals has to be a subset of this across all the space of the precisifications. So remember, this is a model structure. You live here. This is your interpretation J, and you have a bunch of, I don't know, accessible other worlds, which are precisifications. And so every F is G is true here if the subset relation keeps holding all the way up. So here you have the subset relation, here you have the subset relation, here you have the subset relation, and so on. So it's not static, it's supervaluated. Okay. So you have the denotation of every, and I'm not going to comment extensively on the other ones because the trick is always the same. It's just that the relation that is preserved might not be the superset, the subset relation might be another relation R. Okay, so for at least you have that. The things that are F and G, okay, have a cardinality that is at least lambda for all the interpretations that precify the given one. And finally, possessives. Here in generalized quantifier theory, when you deal with a possessive, you typically take an individual, like John, an individual denoted by a term, and you associate with it a relation, which is the relation, just a set of individuals that are connected with John. Take John's cats, for example. And when you take the intersection with the first argument, that has to be a subset of the second one. So John's cats are shy. Right? It's true if and only if the things that are John's and cats are a subset of the individuals which are shy. Okay? And this again has to be preserved all the way up. So that relation there can be complicated. Doesn't have to be as simple as the subset relation. Now, I should put a disclaimer, in English at least and in other languages as well, not every genitive construction works like that. So John's cats are shy works like that. If you want to make it work for John's accountant lives far away, it doesn't quite work like that. But here we don't need it to be precisely tracking these genitive constructions. We need it mostly for technical purposes. Okay, we need that thing here to generate a filter in the algebra. Okay, so now that we have that, let's define operations between functions. We define them in the obvious pointwise way. So let's define algebraic operations. This is a meet, and that's a complement. The joint is defined in the usual classical way. So meet is defined pointwise. So for all j's, it has to be the case that you take the intersection and you take the complement. Let's take a generalized version of the meet, so the infinitary version. And then essentially what you have is this, the set D here, okay, so the quantifiers that you're going to define is the smallest set of quantifiers in my sense, so this set of pairs of function, that includes the basic ones, the ones I just showed, and is closed under complement and meet. So this ugly formulation here is just closure under complement and meet. So whenever you have a lot of other quantifiers, the meet is in there, and we have a lot of other quantifiers, and when you have a quantifier in D, then also the complement is in D. I apologize for the set theoretic notation, it's actually quite cumbersome. Sometimes in GQT you find the lambda notation, which in this kind of case would be less cumbersome. In other cases it would be more cumbersome, so I go with the set theoretic notation. Okay, what's the Keelan-Stadi theorem? Well, this is adapted to the supervaluational structure, of course. We were talking about models in the first order logic sense, but you can lift it up to the supervaluational structures. For every supervaluational structure, the conservative type 1 quantifiers are exactly the elements in D. I'm not going to give you the proof because it would be long. One direction is straightforward, because for that direction here, you just have to check that all the quantifiers in there are conservative, and that's just a check of 3 quantifiers, and that the closure preserves conservativity. For the other one is more laborious because you have to reconstruct the set of all the conservative quantifiers starting from D. And here we have adapted a proof strategy that is in another paper that I have with Michael Glansberg, where basically, which is not that different from the original proof, is more algebraic, but the spirit is the same. You first show that the target set is a complete atomic Boolean algebra, and as soon as you know that the algebra is atomic, as soon as you characterize the atoms, you can characterize every element in the algebra by taking the Boolean operations. So the goal is now characterizing the atoms. And the atoms themselves can be characterized as Boolean combinations of non-atomic quantifiers that are in the conservative set. Now, as you know, the atoms of the Boolean algebra are inclusion small elements of the algebra, so they sit at the bottom of the algebra, and then you go up and you take all the other elements. But here we start from element in the conservative set that are big elements in the algebra. You go down with Boolean operations, you characterize the atoms, and then you go back up. So you do this thing. Yeah. So basically, at the end, you can define everything from the quantifiers in your basic set. Okay, good. Now that we have this, we can finally use the Keenan-Stabi theorem as a definability theorem so that we have an object, a linguistic object, for which to give the supervaluational semantics. And then we test how the supervaluational semantics fares with respect to desirable inferences involving quantifiers. Now, we need now to formulate a language where these quantifiers live, and then we can give truth conditions for these quantifiers. Now, the problem is that the language is not going to be very pretty. The reason is that we have seen that we have to have these three quantifiers, right? We have to have every, at least, lambda many, and basic possessives, and they can be taken as basic constructors of the syntax. Rather than having for all, and there exist, you take a binary variable binding operator, which is every, that's customarily done in GPT, at least lambda many, and the possessives. But the other quantifiers are defined by taking the Boolean operations. And the complement is easy, but the other Boolean operation is an infinitary operation. So you need an infinitary language, a language that allows for big conjunctions of a possible infinite size. Now, you might say, well, I don't like infinitary languages. I want my conjunction to be finite. That's perfectly fine. But it means that you're restricting yourself to a finite domain. If you restrict yourself to a finite domain, then you don't need to construct quantifiers using an infinitary conjunction. There is, an unpleasant consequence of that is that some quantified sentences come out strange. Like, in every finite domain, it is true that finitely many numbers are prime. And it's false that infinitely many natural numbers are prime. And the fact that there are infinitely many prime numbers is a basic theorem of arithmetic, so you would want that to be true. For that to be reconstructed with the infinitely many quantifiers in this case, you need an infinitary domain. So if you don't talk about math and mathematically oriented quantifiers, it's perfectly fine. And just imagine that whenever I write big conjunction, there is a standard conjunction. But if you also want that, then you need the infinitary one. Okay, so the vocabulary contains these guys, every, at least lambda many, which I abbreviate as AL lambda, and the possessive. So whenever you have an individual, John, this is John's. Okay. And they form sentences in the way you would expect. So whenever A and B are sentences, then every formulas, then every AB is a formula where every binds the variable x that they share. The same for at least lambda, and the same for John's. Okay. All right, so we fix a supervaluation structure, and suppose that the domain D has a certain size. You need a cardinal that is at least this big, and then the conjunction will be an infinitary conjunction of the size at most kappa. There is a deep philosophical reason for this choice, which is that otherwise it doesn't work. So because you need to reproduce the Keenan-Stabi construction that uses, essentially infinitary Boolean operator of that size. So it has to work like that. If the domain is finite, then this is also a finite number, so no problem. Okay, formulae are defined in the usual way. So these operators bind variables and form formula in that way, and I also assume a standard syntax for the infinitary language. Okay, now for the semantics. Variable assignments work exactly as in first order logic. It's a function that assigns an object in the domain for every variable of the language, and the X variant is exactly what it is in Tarski and semantics, nothing special. Denotation also works exactly as it does in first order logic. You have a term t. If it is a variable, look at the variable assignment. If it is a constant, look at the interpretation. If it is a function, then apply recursively. And now, this is the semantics. Now, suppose you have an atomic formula, a predicate P applied to terms T1 to Tn, then it is, well, if you have a term, you satisfy in a model under interpretation the formula A, when A is atomic, if the extension of that tuple belongs to the extension of the predicate. Instead, if it is a negated atomic formula, you satisfy that formula if the extension of that tuple belongs to the anti-extension of the atomic predicate. So here is trivalent semantics just as usual. Identity works in the same way. You remember we said at first that we need separate clauses for truth and falsity, and we need that for the quantifier. So we need to do basically negated and non-negated clauses all the way. So double negation works in the expected way. A double negation is satisfied if the formula without the double negation is satisfied. And conjunction and negated conjunction work in the usual way. So a big conjunction is satisfied if every conjunct is satisfied, and a negated big conjunction is satisfied if there is at least one conjunct such that its negation is satisfied. Okay, so everything's fine up until here. Now, this, which is for the quantifiers, I'm only going to comment on every, because the other ones work essentially as expected. Okay, if your formula is every B is C, then you satisfy the formula in the model M under the interpretation J is every J prime that extends J is such that it preserves the subset relation. Just as I said before. Before I had the extension, and this is a truth condition. If instead your formula is not every, then it's satisfied in a model under interpretation if you find, okay, you find some counterexample. Actually, here I have for all J prime, this can be simplified. It doesn't have to be for all. The semantics is done in such a way that if you find one, it keeps being a counterexample. So if you find a counterexample somewhere, so an individual who is B but not C, where the negation is internal, so it's not the case that it is C, but it is not C, then if you find an individual here, then your model and interpretation satisfy not every B is C. The other quantifiers work mutatis mutandis in the usual way. Okay? And here is just the convention for the things that are A. Good. As I said, there is exactly one slide on truth. This is a supervaluational semantics, and if you restrict yourself to classical precisification, you get exactly Kick-Fine style supervaluations. If P is a vague predicate obtains exactly that treatment, you just extend it to all these quantifiers that can be defined. You know that supervaluational semantics can be employed to deal with a self-applicable truth predicate and with paradoxes. It's the case that you can do it here too, with, I would like to say with some limitation, but the honest truth is with many limitations. You can do it here too. So with many limitations, there is at least one supervaluation structure and one interpretation for a truth language, so now you have the truth predicate around, such that true A is satisfied in that structure if and only if A is satisfied in that structure. Now, I am purposefully being vague here because you see that this is a predicate and A here is a term that denotes A. So it means that there is a coding of the syntax. But the language is infinitary. So you need to code an infinitary language. So certainly if your kappa is uncountable, you cannot code it in arithmetic. There are works on the encodings of infinitary language. You can find functions that are delta definable instead of C that do the encoding of essentially infinitary languages of the shape L kappa lambda. And what we need here is essentially L omega kappa plus the generalized quantifier, right? And you find encoding of this much more general languages here that are definable in set theory. So you can encode the syntax that we are using here. I won't go into the details, but it can be done. Okay. This is all I have to say about truth. I'll stop here. But now we want really to focus back on the quantifiers, because you remember we started from some inferences and we were observing some properties and also perhaps some desiderata concerning the inferential behavior of quantifiers. Now, in this particular semantics, this is the non-contrapositive semantics. So all the things that I said might behave very non-classically at the beginning are recaptured in this semantic. So no contraposition, the homogeneity feature, the empty restrictors, and so on. But those were very scattered observations. They were not very systematic. What we want is a more precise answer to the general question, how good is this semantics at recovering classically valid inferences involving the quantifiers? So to answer this question, we need two things. Well, first, we need a notion of logical consequence, because we need to formalize inferences. And then we need a well-understood class of inferences on which there is a lot of work, both formal and empirical, and we use it as a benchmark. Okay. And for the logical consequence, in supervaluationist semantics, you can define at least two notions of consequence, one the so-called local and one the so-called global. The local consequence is a classical one. So gamma locally entails A if for every structure and interpretation, whenever such pair satisfies all the premises in gamma, then such pair satisfies the conclusion. Okay, so that's classical consequence. And for now, we're going to use this. And for B, we will test our semantics on, again, a well-understood class of inferences involving the quantifiers, which is monotonicity properties. Now, these are roughly the monotonicity properties, and they have to do with preservation of the quantifier if you go up or down, okay, in either the scope or the restrictor of the quantifier. Okay. So, for example, the quantifier has this monotonicity property here. If whenever you have the quantifier QAB being true, and you go up, so you take a superset of A, the property remains. Instead, the quantifier goes up in the second component if you do the very same, but not for A, but rather for B. Okay? And the same goes for the other monotonicity property, and they combine in the usual way. To give you a simple example, the quantifier every has this monotonicity property, or as it is called, it is upward entailing in both restrictor and scope. And this is the transitivity of the subset relation. So if you have every A is B, then you can take that B and B is a subset of C, then every A is also C. Oh, sorry, every has this property. Right, so every A is B, B is a subset of C, you can infer every A is C. But if you take that A0 is a subset of A, you also infer that every A0 is B. So you have this property here. Sorry, I got it wrong. So downward entailing in restrictor, upward entailing in scope. Okay. There is a lot of work in generalized quantifier theory on these monotonicity properties, how they behave. For example, this is how they interact with negation. I won't go into that. I just want to take this as my benchmark. And the problem for the current semantics is that we get very mixed results. If you test monotonicity properties in the current semantics, you get some results right, according to textbook benchmark you would want to have, and some results not so right. For example, at least, I'm going to formalize a subset using every, because I need inferences. I need to test inferences, so stuff in the object language. At least is a upward monotonic quantifier, and here the prediction is actually correct. The theory correctly predicts that at least is upward entailing, and as a corollary, you have that plenty of quantifiers that are definable in terms of at least are also upward entailing. Sum is definable as at least one, so it's easy to define sum. Okay, you remember we have at least lambda for every lambda up to the cardinality of our domain. So at least one is sum. And at least omega is what I call IM for infinitely many, at least omega. Those are all special cases of at least, and they're all monotonic in the right direction. So they're all upward entailing. However, as soon as you have negation, you have failures of the intended monotonicity property. So the expected result was that this goes, but it doesn't go. You can find counterexamples. And you have similar story for other stuff that you can define in terms of negated at least. For example, no, not at least one. You define the quantifier no. Should be monotonic in a certain way, but it's not. So you have a bit of a mixed bag here. I have other examples here, I'll just skip over them. So a mixed picture. At least and every satisfy their monotonicity properties, but negating a basic quantifier disrupts the monotonicity property that it's predicted to have in GQT. So since you can define all these conservative type 1 quantifiers for the basic one by negation and conjunction, monotonicity properties are not guaranteed to be preserved from the basic one going up. And it's especially difficult to give a map, a precise taxonomy of which monotonicity properties are actually preserved. Because, for example, if you take a quantifier as a conjunction of monotone quantifiers, like every person and at least 2 cats, that's a quantifier. Every person and at least 2 cats are in the room, something like that. But few interesting quantifiers are defined like that. Most of the time you need negation to define interesting quantifiers. So interesting quantifiers have to be checked for monotonicity individually. For example, most is upward entailing in the scope, as it should be, but it's not, its negation is not downward entailing in the scope, but it should be. So this this is basically what we have, monotonicity behavior and this semantics here. And this motivates a small variant of the semantics. I have been speaking for a long time, so I'll be very short, and I will just present you the result. And the small variant is essentially imposing a modal structure that is more than just reflexivity and transitivity, but is something similar to what you have in hyperintentional semantics. If you're familiar with Hannes Leitgeb's system HYPE, for example, HYPE can also be presented as via modal structures. If you impose basically the HYPE modal structures to the set of possible worlds that we have, which are interpretations, you get a different semantics. And this is what goes on here. To define HYPE, you need to define the Raugli star. But even glossing over all the details, what happens here is essentially that now your accessibility relation is much more complicated, or at least much more stringent, is reflexive, transitive. Crucially, it's convergent. So you start from here, you go to different points, and then they go back to at least one point. And then it interacts exactly in the HYPE way, okay, with the Raugli star. So this is very close to Leitgeb's system HYPE. Okay, it's for supervaluations, but it matters little. If you do here, if you do that, you can define the same semantics as before. You can actually simplify that because you do not need to split positive and negative clauses. And you have a nice result. If you define logical consequence in the global way this time, not in the local way, and the global way is when you expect satisfaction of all the structures for the premises, then you have satisfaction by all the structures from the conclusion. If you do these 2 modifications, so superimposing the HYPE structure and defining consequence in the global rather than the local way, you have very nice results for the monotonicity properties. In particular, you have all of them. So that's the nice result. So suppose that you take a monotonicity property P, so P there ranges over objects of that shape, right? For example, this monotonicity property and that monotonicity property and so on. So P is one of them. Let's say that Q, your quantifier Q, has the property P in a given semantics if the inferences encoding P are valid in that semantics. For example, every, as I said before, has this monotonicity property P, because these 2 inferences are valid in generalized quantifier theory. Remember, this is just the transitivity of the subset relation. So the result that you actually have is that for any conservative type 1 quantifier and for any monotonicity property, the quantifier in question has that monotonicity property in the classical semantics if and only if the same quantifier has the same monotonicity property in our semantics. So we have 2 competing systems. One that is way more non-classical, right? It doesn't have contraposition, it has all the things that we said at the beginning, but because of the failure of contraposition, the non-classicality basically percolates to the monotonicity properties, and if you want monotonicity properties, you don't have them. Here instead, if you impose this stricter modal structure and you define consequence in a different way, you do not have all the non-classical things that I said at the beginning. You are very classical there, so you give the classical response, but you have monotonicity properties. So it seems that, yeah, okay, so this is the monotonicity behavior under, oops, old one, under the KS3 semantics. Okay. So these are very preliminary results. I mean, we haven't checked all the relevant classes of inferences from the literature, but we have taken them off the shelf, essentially, and they do not yet show that this theory captures every possible inference involving quantifiers in the classical way. But it shows that a substantial portion of the classical theory of quantifiers can be recovered within a non-classical framework that accommodates weakly naive predicate and all these supervaluational treatments of indeterminacy. So, depending on how you adjust the modal structure, your supervaluational semantics can be further away from classical inference patterns or closer to classical inference patterns. That all depend on adjusting the modal structure. This is why I think it's important to view at least this brand of supervaluation as incorporating a modal structure of some sort. And so I presented two systems, as I said, they are competing. From the way that I presented, you might think that I have wasted your time because it seems that the second one is better. But actually there is a genuine trade-off, right? And the genuine trade-off is this. If you take the first one, it's immediately possible to define a conditional operator from every. So as soon as you have every A is B, you can translate that as, if A then B for a conditional operator. And the conditional operator that you have is actually very nice. It obeys the deduction theorem. It's essentially an intuitionistic conditional, even within this non-classical framework. In the other, much more classical framework, as far as inferences go, you get a terrible conditional that doesn't behave very nicely. Certainly doesn't validate the deduction theorem. So it depends which way you want to go. You want to go very non-classical, you buy a non-classical conditional that behaves very nicely, you buy the non-classical solution to the examples that I presented before, and you lose monotonicity. You want to go more classical, you stay classical with the response to the examples that I said at the beginning, you regain very classical inferential behavior for the quantifiers, you cannot define a conditional from every. So if you think that there is a very close connection between if, then, and every, then you might want to define the conditional from the quantifier. I personally don't think that you should define a conditional from every. That is my take, but people might have different views on that. So this is a bit more of a picture. In both, you can have the truth predicate that I mentioned before. So both are non-classical. None of them coincides with classical logic. Otherwise, you wouldn't have that truth predicate there. One is more classical when it comes to the monotonicity properties. The other one is more classical when it comes to the conditional that you define using the every quantifier. So maybe there's a trade-off. This is something, of course, to be discussed. That's it. Thank you very much.
Thanks, Lorenzo. We take 5? Perfect.
Yeah. Okay.
See you.
Okay, and also I can say out loud, because there have been some folks online, so if you have questions coming in from online, don't hesitate. I'm watching the chat. I can relay questions. Good luck if you need to write formalism in the YouTube chat box, but other than that... That's it. Yeah, actually, honestly, I read LaTeX, so you'll actually be fine. I speak LaTeX.
So is there any question?
I have some.
You can you can look it up for sure.
So yeah, I think this is a very nice project, and it seems very natural to find some indeterminacy there and then try to deal with it. But I was like very fascinated by the two different semantics you get in the end, and it seems like it should not be a formal decision which one is the right one or something, or it's for some property. Like in the first system you showed where when all these things fail, and I think it's weird, intuitively it's weird for me to see these as benchmark cases, like, oh, logic has to do those things. You know, you're in a kind of weird situation, so we are exactly interested in where the inferences are going to fail because of the indeterminacy, like counterposition. So I would rather think it natural to look for the reason why it fails, and then see whether this is, because there's no decisions making in the semantics into it that I see that are very unnatural or something. So I would expect that if you tell the story, like actually you could find convincing cases of why the benchmarks should fail. That's a good thing.
That's an excellent question. I don't have a satisfactory answer, I'm afraid. I think that, so there is, maybe I can split your question in two, but maybe I can say first something about if and why these inferences are expected to fail, if at all, and then how this links up with features of the semantics. Whether they're expected to fail, it's an extremely tricky matter because it has to do with linguistic intuition, and even there, first of all, as far as I know, I don't think that there is experimental evidence on these particular things, just because as we were briefly discussing now, there isn't a lot of work on generalized quantifiers in the presence of indeterminacy. There is very well-established literature on general features of generalized quantifiers, linguistic applications, and so on, but not so much on the non-classical side, let's say, and how they can be defined going away from classical logic, but try to retain at least some nice features, inferential features of classical logic. And so we have to rely on judgments here. And here the judgments, in a way, are very, not very telling, because there is a lot of phenomena that are stacked up. For instance, here there's presupposition failure. And if you insert like presuppositional sentences into an every construction, and you have a certain kind of intuitions about presuppositional triggers, then you might end up rejecting sentence number 2. But you are testing a lot of things at the same time. You're testing the intuitions that you might have on presupposition in the context of a contraposed every statement, right? Here, category mistakes. Category mistakes is it's its own field, and people have widely diverging opinions on what the right semantics is for category mistakes. And here you might think that no, in that case, I would be perfectly happy saying everything not on Earth is not expensive, because it's not for sale, so a fortiori is neither expensive nor cheap. Obviously, you can retort, well, but I also want the inference that every non-expensive thing is cheap, right? If you want that inference, then presumably you cannot answer the way I just did. But it's extremely difficult, I think, to find conclusive linguistic judgment in the absence of empirical work that has been extensively tested this thing, and also in the presence of a conflation of all these phenomena. Because quantifiers are higher level, so they need a lot of input, to be worked with. And here, the kind of indeterminacy is in the input, is not in the quantifier. The quantifier by itself doesn't do much. This case can actually be a little bit different, because in this case, the quantifier does something, but this is really piggybacking on the conditional. So really what's going on there is that you have a lot of patterns that are well known from the literature on conditionals. Something I didn't mention, for example, is that you can find versions of the paradoxes of material implication for quantifiers, right? It's very easy. And you would have similar counterexamples. So there, the people who think that every and if then are closely connected will point to these kind of cases, right? If you have something like this, you might say, well, yes, there is an indeterminacy in the quantifier, but again, first of all, I think the majority of people who work on indicative conditions in natural language think that indicative conditions do not contrapose. But there is also a literature of people who think and argue that indicative conditions do contrapose, and there is a hidden concessive in apparent cases of failure of contraposition. So when you have an apparent failure of contraposition, you're talking about even if rather than if. There is a literature on this, so you might think that something like this is going on there. So this is just to say that we've tried to elicit some intuitions by considering examples, but they are far from conclusive. So it's nearly impossible, I think, to take them to be a real benchmark that discriminates between the two semantics. That's why they are like ways to get going in a way, but the second kind of cases, the monotonic inferences, which are very well established in the literature, I think are more robust from the point of view of where evidence comes from and what kind of evidence we can muster. I don't know if that answers part of your question, at least.
Yeah, partly, but it seems like it's not because our intuitions are like quite incoherent and so on. We are just bad at lots of nesting and these things. I mean, when there's different linguistic phenomena that are complicated and we have to combine them, and we're a bit troubled and intuitions go in all directions. But that doesn't mean that you, as philosopher, cannot give like normative theory of why it should be contrapositive or whatever, or monotonic in that sense, and I find it very interesting that for reasons of pure indeterminacy, which you can take to be independently justified, you lose this monotonicity features.
Yes.
And then you can, like, even if maybe intuitions are not supporting this at all, you can say no, but in fact, it should fail this monotonicity, and I have a good argument for why it should fail. Why it's like actually incoherent to assume monotonicity in these cases.
That's very interesting, and it's connected to what I said, because if you look at the proofs of the counterexamples where you show that you can have that you have structures that satisfy the premises of the monotonicity inferences but not the conclusion. If you look at the counterexample, obviously this is just one counterexample, so it's as informative as it goes only a certain way. But if you look at the counterexample that we came up with, is like, oh, if I only had contraposition, I wouldn't have this counterexample. So it's closely connected to the failure of contraposition. Failure of contraposition makes you lose monotonicity for the negative quantifiers, for the negated quantifiers. So this is something that you can use to, let's say, bolster your case for, let's say, I should lose these things because they stand and fall together, and indeterminacy basically undermines them both. I'm maybe a bit more hesitant to give a strong normative tone to this work, because it's linguistically motivated, and so unless you have, specific natural language independent goals in mind, like, I want to teach a machine to think along these lines, or I want to set up an artificial language that for my scientific reasons behaves in this way, if you want to go back to natural language and say, look, you should take very seriously these cases of indeterminacy, as seriously as they have been taken for vagueness, presupposition failure, anaphora, and a lot of other language phenomena, because they also arise in quantifiers. But at the same time, you should provide a theory that is a workable theory of natural language, that accords with linguistic judgments more than it orients them.
I mean, this may be a very programmatic discussion, but I don't agree. I mean,
You would like a more normative, but even for natural language?
Yeah. So then we say we have mixed intuitions about it. I mean, our intuitions might be wrong, but I have a good argument why they should be wrong, and then it will guide you to better reasoning if you don't use contraposition in those cases, or you don't use the monotonicity feature, because there's a danger that you make an error. In natural language, right? Because it's gonna lead to errors, right? If you apply contraposition in these cases.
Yeah, you can apply along these lines and say, well, yeah, if you reason fully classically in the cases where you would expect a quantifier to be monotone when it's not guaranteed, you end up with a classical conclusion, but the classical conclusion is wrong because maybe it's something like that. The classical conclusion tells you that both these sentences are true, and it's clearly incoherent. So, given the context, this is the context, these two sentences, I cannot envisage a situation in which they're actually both, a scenario in which they're actually both true. So you would do a more normative / metaphysical, I suppose, line of argument and say you wouldn't end up something like this, and that's actually a mistake. Yeah, one can do that. Yeah. I mean, in fairness to the classical theory, these cases are discussed, and there is, a discussion of it's recognized that the fact that they're both true is bad, but typically it's assumed that quantifiers have a presupposition of a non-empty restrictor. So if I say every A is B, is assumed that there is at least one A. Which might be strange in some occasions, because you can say that, every unicorn lives here and every unicorn doesn't live here, and they're both false. Or both true, depending. In the, let's say, traditional situation would be both true in the Aristotelian case, in which you assume that there is at least one unicorn. In the other case, it would be both false. So, yeah. You can argue more normatively like that. I prefer to try and elicit an intuition whereby in any given scenario exactly one of these is true and the other one is false, and it's not the case that they're both true and it's not the case that they're both false, because I think it accords more with the intuition that come from the debate on indeterminacy. But that debate is also theory laden, so it's not fully natural. One other way you can argue for this kind of conclusion is a sort of holism. And you can say, look, we have a number of indeterminacy phenomena, and we have a number of semantics to make them work in this or that way. And this is a way of showing that the indeterminacy-friendly semantics can go a long way towards capturing inferences that exceed first-order logic.
Mm-hmm.
So, yeah.
Great.
This would be one way of arguing about this.
Good.
Yeah.
Other question?
I have other questions, but unless you have.
Yeah, I have a little one. Maybe just out of curiosity, you spoke about type of quantifier 1 and 1-1.
Yeah.
Is there other in natural language?
That's a very difficult question, and I'm
Sorry.
very ill prepared.
Oh.
So yes, yes, but it's kind of difficult to come up with. So, for example, people have argued that reciprocals are they type 1-1-2 quantifiers? I should check it out. I should look it up. But reciprocals like each other. If I say they hate each other or they like each other, then you're basically talking about two people and the relation between the two people. So I think that's occasionally has been modeled as a type 1-1-2 quantifier. That was literally the best example I could come up with. I think that definitely it has been studied, but I think the most common case is the type 1, just because it corresponds to the category of the determiner. So something you use together with a noun to make a noun phrase, like every dog, and then you put a verb and you do a verb phrase. Yeah, I think so. Even the purported counterexamples to these claims, like to the claims that these constructions are conservative, they all involve type 1 quantifiers, because the counterexamples have to be determiners, or at least it can be argued to work like determiners. So if you disagree with the conservativity universal, you have to come up with the counterexample, but that also has to be something that functions like a determiner, and that is modeled by a type 1 quantifier. You can cook up quantifiers mathematically of any kind. I mean, it's super easy to quantify to cook up a type 1 quantifier that is non-conservative. Just the superset relation is not conservative. The subset relation is not. The superset relation is not. But the question is, does it correspond to something in natural language? So in natural language, in nature, do we find these quantifiers? And the wisdom seems to be no for the conservative case, and very little for the cases that exceed type 1 or type 1, or relatively low types anyway, like for reciprocals. Yeah.
Where are you?
No.
Already asked one. Yeah, so I was wondering whether so if I understand well, you can deal with both cases where there's some phenomenon of the indeterminacy already there, and then you add some quantifiers on top of that.
Yeah.
You quantify in these kind of contexts,
Yes.
About these kind of contexts. That is one seemingly very useful application. And then there's something else where the quantification, the generalized quantification, causes the indeterminacy.
Yeah.
And I did not see in the semantics very well how this difference, like I would expect like two levels of supervaluationism or something like that. Like you have on the lower level, just the propositional level, already some supervaluationism.
Yeah.
And then when the quantifiers enter, you also consider. Does that make any sense?
Yes, it does. We didn't think about it this way, but because essentially what is supervaluated is mostly the quantifier, in the sense that if you look at the semantics, I'm just going to take the first one for simplicity. At the base level, there's just the trivalence in a way, right? And then when you supervaluate, you look at the extension for the quantifiers. You don't have to do this. If you do this, what you end up with is basically strong linear logic for this framework, for this language here, and a supervaluated quantifier semantics that gets definitely more classical than strong linear logic. For example, in a pure strong linear logic setting, the sentence "every A is A" wouldn't be true, whereas here it's true. Because look at any extension that you want, A is a subset of itself. And if you take this to define a conditional, you get essentially the intuitionistic conditional. So if you put them together, you get a Thomason logic. So with the strong cleaning base for the Boolean and the intuitionistic conditional, at least for the like the sequent calculus presentation, you would get that. So you supervaluate only here. If you want, you can also supervaluate here. Nothing prohibits that.
And that's what feels more natural to me.
You can do that. You can definitely do that. And you can get essentially all the ranges of supervaluationism also at the basic level. So here you can supervaluate in the classical way and you get classical logic in the same sense of supervaluationists. So not classical semantics, but the classical logical laws, etc. If you don't, instead, you have only here the supervaluation.
Yeah,
but you can do it
so
both ways.
excluded middle doesn't work in the logic.
Here, no.
Yeah.
But if you supervaluate here, yes. So, for example.
No. In that case, it does.
Yeah.
Rather, the logic you presented, in general, excluded middle is not valid.
Exactly, because of the strong cleaning behavior. But there is an easy modification. If you do like, whenever A is an atom or not an atom, and then you prove it by induction, rather than merely checking that this belongs to J plus, you ask that it belongs to all the ones that extend J plus, and you also ensure that every extension is total, so it's classical. So they don't overlap, but they exhaust the domain. In that case, you would have the excluded middle and all the logical laws. But that's a very good observation, because here it's really a hybrid between a highly non-classical, strong cleaning line for the Boolean connectives, just because it's simpler. So,
just because it's simple.
Yeah.
But the simplest would be that it's just classical on the level of not quantifiers, right? So you choose to allow indeterminacy there.
You can do that too. It would lose you the possibility of having the truth predicate behave in this way.
Sure.
But you can. And you can be fully classical at the ground level and supervaluational at the quantifier level. That actually is a very interesting observation, because these two levels can be completely disconnected.
Yeah.
So if you want, you can disconnect them entirely. So for example, you can have cases where for every propositional A and B, A or not A holds, B or not B holds, and every classical logical holds of A and B. But you can have, for example, that it's not the case that every A is B or not every A is B. That's fine. That you can have that.
Was there a reason why you did not go that way?
Because like the simplicity, but the classical case, you mean?
Because people have always presented supervaluationism as a kind of a way to restore classicality and so on, and then it's kind of a bit schizophrenic or something to
if you do it
start already from a very weak logic.
Yeah.
So that you'll never be able to recover classical logic anyway, and you recover some classicality.
You can if you supervaluate the basic weak logic.
I do see that. I do see that. I just wonder why you did not.
It's probably because we wanted to treat all the things simultaneously, including the truth predications. To behave in
this
that way.
truth predication.
Yeah. So this is a bit of a middle ground
program. Yeah. I see.
So if you want that. That's a natural way to do it. Then, of course, you have to be a little bit careful, because you can formulate Carey-like paradoxes with the every quantifier, with the type 1-1 quantifier. That has been done. There's a relatively recent paper by Bruno Whittle on that. And actually, the paper that I mentioned in passing before, the paper with Michael Flansburg, it's a paper where we do a formal theory of truth for generalized quantifiers. But then there is no classicality recovering, and not even supervaluation. Here, it's supervaluation. Right? But I should emphasize that these two levels are, at least as a matter of principle, independent. And also the fact that if you do things like this, you can isolate exactly the kind of indeterminacy that arises exactly from the supervaluational quantifier. Because from the supervaluational quantifier, you can have exactly the features that I was mentioning at the beginning. So if you want exactly one of them to be true and the other one to be false, you can have it, even if the basic logic is fully classical or the basic logic is fully strong cleaning. It doesn't matter. It's independent. So you can easily recover whichever intuition you prefer for that pair of sentences. Thanks, I should remember that.
The talk will be online, so you'll have access to everything.
Okay, cool. Thanks.
Okay. So sorry if you said so earlier, but I was wondering, and you said just before you developed another strategy at one point. Why supervaluationism? We spoke about the strategy before.
Why supervaluationism here?
Yeah, I mean, like, could you have chosen the logic we spoke about this morning?
Revision theory.
Yeah, I don't know. Like, what was your process in it, or is it that you were like, okay, supervaluationism looked like the best tool?
No. My process was much simpler than that, and it is that if you want to do a revision theory of truth for, let's say, non-monotonic connectives, it's already very difficult. So if you want to do it for generalized quantifiers, it's even more difficult. So my thinking was supervaluationism, easy, I do that. The revision theory, much less easy, I won't do that. No, but this is a joke. But it's really something that is natural to mention. Actually, when we submitted this paper here, which is still under review round 2, one referee said exactly what you said now. One referee said, "Oh, this is nice, but this is Stronclini based. So in the end, you get all the issues for Stronclini based theories, which are either very non-classical, if you want a certain behavior of the truth predicate, or squeezed onto classical logic if you want a different behavior of truth predicate." One very new thing to do that would be quite interesting would be a revision semantics for all of that, and. I just don't know how that would go. I mean, presumably one can do that. Really, you have to, you have to combine. You have to combine the Stronclini semantics for the quantifier that we have there with a revision sequence. But developing this theory would take much longer than it took to develop these. And this is a very natural next step, because essentially what we are doing is lifting to the generalized quantifier level certain approaches that have been explored in detail at the propositional level, and even the first order level. But the generalized quantifiers are very difficult to treat in full generality, because a generalized quantifier by itself, it's a relation, it's a set of ordered pairs. So it's an arbitrary object as it can get. So this is just a type 1-1 quantifier. This is why we restricted ourselves to the type 1-1 quantifier, because you can generate them in a relatively easy way using the Keenan-Stavy theorem. The Keenan-Stavy theorem, I don't know how would that look like in a revision setting. I don't know. I have to think about it. On the top of my head, it looks really complicated. But this is, as I said, a very natural question. So natural that the referee for this paper asked the very same question. And it's absolutely something to be looked at. But we wanted to gather some evidence of how these quantifier logics look like by first developing them in frameworks that are very well known, like the Stronclini framework and the supervaluational framework. Yeah. Thanks. This is an excellent question.
I have a really naive one. So coming from as someone who hasn't been thinking about this stuff in 15 years. But one thing you said at one point, so you mentioned that you and forgive me because it went by fast, so I've already lost at which point in the talk it was. But you mentioned that that you keep tabs on the empirical work around the use of these kinds of, around use of phrases like this in language. And so this may come back a bit to this descriptive normative point that you were talking about with Peter earlier, but I'm just interested, how does that inform what you do? How has that actually kind of, and sort of what is out there? I imagine this is, so this is stuff coming from the corpus linguists, or who works on this stuff, and in the sense of figuring out how real humans use these kinds of complex constructions.
Okay, that I am really ill-equipped to answer. So what I know is this: is that there is a lot of work on the formal semantics, and that's like a logic language interface. There is a lot of work on the natural semantics, and so testing whether the theory captures ways of using the quantifiers that are actually out there, like the monotonicity case would be a prime example of that.
Yeah.
And there is a lot of work on comparative linguistics, testing, for example, whether the universal is actually attested across languages. So you go to languages whose syntax doesn't even have determiners working in the same way as they do in English, for example, and you check whether you can still explain essentially something that takes the place of determiners in those languages by quantifiers that are conservative. And there, I briefly mentioned that there seems to be a very strong evidence in support of the conservativity claim. Cool. I would say these are the three areas. So the logic language interface, which would be where I would be more comfortable. Right. The empirical semantics, actually checking, whether the predictions are right in a single language, and then comparative linguistics, checking whether they hold across languages. If you look, for example, the textbook reference that I have been using is the Peters and Westerstall book, Quantifiers in Language and Logic. It was published in 2006 by OUP. And there is a first part that is on syntax and also on a lot of different languages and quantifier construction. It was very fun. I remember reading about quantifier construction in native languages of the Canadian Arctic, of which I know close to nothing. But what they were explicitly trying to do is gather data from languages that do not resemble each other, or resemble each other as little as possible, because they have different histories and so on. And they do mention some applications there. That being said, it's just chapter 1 with some info, and then the bulk of the work is at the logic language interface. But they do cite a lot of relevant literature. Another piece of literature that might be more empirical is the one that I briefly alluded to, the counterexamples to conservativity. There is one counterexample that is debated a lot, even though it's not super common to find papers on generalized quantifiers in linguistic journals as it was maybe 30 years ago, at least that's my impression. There was a relatively recent paper discussing the case of only. Only has been proposed as a possible counterexample to the conservativity universal, because arguably only, if it is a quantifier, corresponds to the superset relation, not the subset relation. If I say every is a subset, every dog is friendly, take a dog, that dog is friendly. If I say only dogs are friendly, that's the superset individual, right? So take a friendly individual, that individual will be a dog. So maybe some dogs are unfriendly, but definitely taking a friendly individual, that's individual is going to be a dog. Okay, and that's easy to show that it's non-conservative, just because in general conservativity fails there. And people have wondered, okay, what do we do with this? Is this a genuine counterexample to conservativity? And so we just throw it away because it has a counterexample, or we keep conservativity. And they have observed that every, or most, counterexamples to conservativity tend to pattern like only. You have counterexamples that work in a similar way and are really synonymous with only. And they have also observed that these counterexamples, in the case of only, is especially clear. In other counterexamples, it might be a bit more tricky, but they tend to admit syntactic functionings, and this would really be either intra the same language or infra different languages. They tend to admit syntactic constructions that are unavailable for genuine determiners. Take the sentence, really out of my depth here, I'm not a linguist, just a logician reading some language every now and then. Take the sentence, I saw him on. Take the sentence, I saw him on the train. Right? If you take this sentence here, the word only can go essentially everywhere in that sentence. So you can say, only I saw him on the train, or I only saw him on the train, I saw only him on the train, I saw him only on the train, I saw him, well, you can put it here, but you know.
Yeah.
Well, only the train? I think it works.
I saw him on the only train, yes, I can put it here. Okay, so you can put it almost everywhere in that sentence. Now, find a sentence where you can place every in as many places as you can place only.
Yeah.
That's not going to work. So they have some linguists have proposed that only is not a determiner, is what they call a polymorphic modifier, because it modifies a sentence but in a polymorphic way. So it doesn't modify the sentence always in the same way. And so this is syntactic evidence that only shouldn't be treated as a determiner, so is not a quantifier, so is not a counterexample to conservativity. So this is the kind of more empirical syntactic literature that you can find.
That's cool. Thanks.
You're welcome. I have exhausted my knowledge of this. So this is all I know.
Perfectly fine. Thanks so much.
Okay.
I have a question about the Faroese students.
We have none of them.
No, I assume that you had none of them. That seems important for yourself.
Yes.
So as a relevantist, this strikes me as not something you want to solve supervaluation in a supervaluationist way.
Fair enough.
Especially not given the fact how you justified that it might fail.
Right.
Or it might be indeterminate. Because you said like, yeah, but if there had been Faroese students, then Matteo would have interviewed them.
Right.
And so what you're looking for is an intentional relation between the Faroese, the being an applicant, and specifically Faroese applicant, but that doesn't matter then, and the fact that it's all handled or interviewed by Matteo.
Good.
Right?
Good. Yes. Right.
And so, like that's my intuition that you should not have a simple supervaluationist solution for it. And my first question would be, do you agree or like how you set on this? But how is there any literature about more intentional generalized quantifiers?
Okay. On intentional and generalized quantifiers, I said yes because I thought you were going to say intentional quantifiers, and I said yes, there is. Intentional generalized quantifiers, no.
Yeah. But that's what I'm very interested in. It seems important to understand language that we get these.
Definitely
more interesting.
I think we might be closer in our respective positions than it looks, because in a way I wanted this to be intentional. Okay, let me say this. There is a literature on intentional quantifier. I mean, I'm not just having in mind like linear logic or these other technical literature, but for example, recent work by Lindström and others on non-instantial generality. So their idea is that there are forms of generality that are not based on the instances. And so here, it's not the case that this is true because we have Faroese applicants and they're interviewed by Matteo, or we have Faroese applicants and they're not interviewed by Matteo. But it's to do with the relation between being a foreign applicant and being interviewed by Matteo. And so this is not based on the instance. And this is perfectly fine. We wanted to recover that phenomenon by being less radical than Lindström is, and possibly less radical than some relevantist approaches are. Because we wanted to say, yeah, you can do that, and you can view it intentionally, where intentions are cashed out as, possible worlds, which are, each of them is an extension. So here, you can do that. You can imagine that this is an intentional treatment because it's different extensions for the functions corresponding to the quantifiers. And the meaning of the quantifier, however, is given by the intentions, quantifying in the relevant modal way over all the accessible functions. So it's not that there is, let's say, a relation that is irreducible to extensions. It is reducible to extensions, but in a quantified manner. And the meaning of the quantifier Faroese applicant, for example, is given by that intention. So it's more classical Carnapian intentionality than it is relevantist intentionality or the potentialist intentionality that Lindström has in mind or one of these things. So it's still intentional, but in a way it's reducible to sets.
So is then right that the thing I interrupted you about during the talk, whether there actually is a difference between this age and smaller than relation, it becomes very important here. Because you wouldn't be able to deal with such intentional cases, if it was a merely supervision evaluationist project, but
Yes.
actually it's a modal thing.
Definitely, absolutely right. It has to be a modal supervaluational semantics. So,
Yeah. Now that is very interesting.
I think this is, and this is something that my co-author has developed independently in a paper of his, like this way of doing supervaluationism in this sort of modal fashion. And you can apply it to a variety of contexts, including conditionals, modals, now generalized quantifiers. And I think that maybe this is to my view at least, is the more natural way of doing supervaluation, because you consider the space of precisification as if it were a model space. So you're much more free to be classical, non-classical, classical at certain points, not classical at other points. What matters is that there is a structure on the space of precisifications, a modal structure. The simplest one is reflexive intransitive, and it gives you a wildly non-classical behavior that answers possibly part of your previous question: where does the indeterminacy of quantifiers come from? It comes from the structure of the supervaluational space. If you instead impose something more classicalizing, like the negation via the Routley star, convergence on the frame, and so on, like Lightcap does in his system hype, then you become closer, you get closer to classical semantics. But really, the indeterminacy in the quantifiers comes from the modal space. And so it's still an intentional semantics in a way.
Right.
But it's a reducible intentional semantics. In the end, everything boils down to sets, which is what we want because we are sort of classically minded. Lindenberg, for example, wouldn't want that. Would say, no, there is a non-set-based generality. The generality has to do with something that has nothing to do with set membership. Our position is more classical in that respect, but you do construct sets of sets of sets, and you give the quantifiers an intention in addition to what happens in the classical case.
Good.
Yes.
Thanks.
I should remember that too. It was a very good observation. Has to find its way into the motivation, I think.
Question. So
You don't have questions anymore?
No.
Do I have other questions? Well, maybe not that are very pressing. Not as pressing as this irrelevancy that shocks me. Well, no, maybe continuing on the previous conversation, so there's some intentionality you can handle.
Yeah.
You have any idea how much intentionality? I mean, is there a kind of cases that clearly call for intentional generalized quantifiers that you can handle that obviously existing projects can't?
I mean, the cases will be exactly these, where you have empty restrictors.
Sure.
Empty restrictors. I think there is like an entire chapter of the theory of quantification that should be rewritten, that's my opinion, on the empty restrictor issue. The empty restrictor is treated in bulk. Either they're all true or they're all false, and there are pragmatic criteria as to why it's inappropriate to utter quantified sentences with empty restrictors. But I think there are a lot of cases in which you can form all the Lewis-inspired counterfactual examples involving empty restrictors. So this would be a case of, I think, an intentional, not the quantifier is intentional, but a case in which the interpretation of the quantifier reveals the intentionality. Suppose that I say every person who walks more than 10,000 kilometers in a day walks more than 5,000 kilometers in a day. Now, no one walks more than 10,000 kilometers in a day, but that seems analytically true, just because 10K is more than 5K. But if I tell you every person who walks more than 10K walks more than 20K, is that true? That's weird, right? I mean, depends. It seems that there is a counterfactual consideration in there. So if there were to be a person who walks more than 10K, or if you're still knocker, you go to the single closest world where this is true, and certainly there you have walked more than 5K, but maybe you have not walked more than 20K because you go to the closest one, so you have maybe walked 10K plus 1 meter or something. Then Lewisian consideration kick in, it's 10K plus 1 meter plus half meter, blah, blah, blah. So you maybe do a set of possible worlds. But regardless of the specifics, this is really a case where you want like an empty restrictor case like this to behave in two different ways. Like 10 more than 5, yes, 10 more than 20, probably not. And this, I think, shows that there is an intentionality in there. You can capture that here, but you're reducing everything to sets. So in a very classical fashion, you're constructing these intentionality out of sets. You might think that this is not intentional enough, and absolutely fair enough. The theory...
it depends if you can get the results that...
you can definitely get this result.
That one, but like it's then the question like how... I expect that you would get some paradoxes at some point, or very counterintuitive cases if you make it complex enough. But I cannot justify. And that's why I asked the question, like how much can you do with this classical solution?
That I don't know because we haven't explored that far. But what I can tell you is that definitely this semantics here, which is basically a variant of, at least for the modal structure, not for the specific clauses, but the modal structure is a variant of hype. This is well equipped to deal with hyperintentional operators. So if you want to add a C in operator, assuming that C is a hyperintentional verb, then you can add it here. I have no idea how far that goes for quantifiers. So I can think of examples of intentionality in quantifiers. I don't know if there are examples of hyperintentionality in quantifiers. If there are, then you're living somewhere in the vicinity of this.
Yeah, that's good.
But if you have an example of a clear hyperintentionality case, maybe you can cook up one using
it like that. But
yeah.
Sure,
maybe one can cook up one using hyperintentional verbs like C.
Yeah, sure.
Yeah. The hyperintentionality there, however, wouldn't arise from the quantifier as it does in the case of the empty restrictor for the intentionality. It would be more like the first family of examples where you take already an indeterminacy trigger, presupposition, failure, category mistake, what have you, and you put it into the context of a quantified sentence.
Yeah, sure.
Yeah, but I also have to probably distinguish, that's a very helpful thing, the cases that you said before, like where the indeterminacy comes from what you feed to the quantifier, or where the indeterminacy comes from the way the quantifier behaves.
Yeah,
like
it's
with
a different project.
You're right. Yeah, I agree. I agree with that. Yeah.
Thanks for the question. Lorenzo, thanks again for coming.
Thanks to all of you for having me. It was such a pleasure. Thank you.
Okay,